thank you for the introduction. Yeah, so this was joint work with David Binder, Julian Jabs, and Klaus Ostermann at Tübingen. Okay, so let's jump right in. So I promised you symmetric data and Codata, and to begin with, so let's think of data as just being something that's defined by having an enumeration of constructors. Can we? Yeah. And similarly, Codata to be symmetric, right? So we want to define this by having an enumeration of its destructors. Okay, so usually if you have this kind of representation of your data or Codata, you usually run into the problem that one of those two will be hard to extend. So if you have data, usually adding constructors is not that easy because you have to kind of run throughout the whole program. And similarly, if you have Codata, it's the opposite. So in this sense, if we just want to talk about data and Codata, we would like to frame this expression problem by just saying, well, if we want to define something, do we want to define it as data or as Codata? Because either way we choose, we will run into this problem of having difficulty in extending. Okay, so why would we want to have to decide on this? Why not just have both? All right. So in order to get a way to do both, we have created a small language which does have both data and Codata, which is set up in a way so that it's easy to work with. And we have a way to switch between having something represented as a data type and having to represent something as a Codata type, which we call destructurization and constructorization respectively. So if we have data and we destructurize it, afterwards it will be something that is kind of defined by its destructors, and the other way around is the opposite. And going back and forth should, of course, be the identity. And it should also preserve semantics in some way. And we also added local matches, a co-matches for good measure, because that's kind of one of the basic things you usually want to have. And it's something that is not immediately obvious how to do in this setting. Okay, all this stuff was implemented in Coq. So the whole thing was, and it was most of the theorems were also verified in Coq, and there's an extraction for Haskell, which I can show you in the demo right now. Okay, so let's just look at some really simple program. So here on the top, we just have some standard definitions of data types, bool and nat, natural numbers, and we have some functions on those. Most of you probably think that those look kind of odd, and that is on purpose, because those things that are called cfunds have some kind of special distinguished type in the beginning. So if you look at the if-then-else cfun, for example, so first of all, cfun is just short for consumer function. So given a data type, what we can do with it is usually dispatch on what is the constructor that's kind of in use here, and then do something according to which constructor we have. Of course, in the example of an if, you usually, if it's true, then do one thing. If it's false, do the other thing. And every consumer function will do this for exactly one data type. So in this case, if then else, of course, will dispatch on bool. So it will. So we write this in a different way to make sure that this one argument is the one argument that is pattern matched on later. All right. So. And the way we then apply this is by doing this something like this at the bottom, which you probably can't all see. So like this. So the distinguished type, we'll just write a term for this type, and then a dot, and then apply this consumer function to this. And the other arguments are just standard argument passing, as you would expect it. Okay. So I also promised you transformations between those, so just do this. Since this is all data types, the only thing we can do is switch them to Codata types, i.e. destructurizing them. I will do this with bool right now. And if you now look at this and you have maybe looked at code before, you will see that nothing that was kind of involved data changed. So the data type for, nothing that involved the natural numbers changed. So the nat data type is the same as it was before. And similarly, the function, the addition function for nut also was the same. However, everything that involves bool is kind of pretty different now. So instead of a data type, of course, we have now a Codata type, which was the whole plan. And how is it defined? Well, we just took this consumer function we had before and just took this as being a destructor for this Codata type. And similarly, we took the constructors for this and made them into something new, which is at the bottom here. What happened? Okay. All right, so what's going on here? Now suddenly we have something that looks very, very similar to our consumer function we had before. It's just the opposite. So instead of pattern matching, it co-pattern matches on our Codata type. And instead of being a consumer, it's now a generator because it generates Boolean values, true and false in this case. So it's two functions. How should we explain those? Well, you can explain it by saying, well, if we have this true, and we apply any destructor to it, we should specify what happens when this destructor is used. In this case, well, we only have one destructor. It's if then else, and it has two parameters, x1 and x0, x0 and s1. And if it's true, well, then we should just return the first one. Okay. And similarly, false will just give the second. But now, coming back to extensibility, I mean, this is not something you usually see. You wouldn't usually write your Boolean data like this. But suppose you have, for some reason. And now you realize, well, I would like to have additional functions on bool. Usually you would then have to add a new destructor here, and then kind of add this destructor to every generator function that's defined already, which could be lots. In case of bool, it's just true and false usually. Well. But we already have seen the solution, in a sense, because we can just go back. We just constructorize again, and we have the exact same program as we had before, just might be a bit mangled now because the order changes sometimes, but in general it's the same. So now we can just add a function. In this case, we just want to add a negation function, which takes a bool, returns a bool, and, well, switches them. Okay. And now, it's pretty unsurprising what happens when you do the destructurization again. So now, we're here again, and it seems like nothing much has happened except for exactly what I wanted to do. I just wanted to add a new destructor, and this is what I've done, but I did never really add a destructor in this sense, but I switched, did something else, and came back. Okay. So, what else can we do? I also talked about a bit about local matches and how they might fit in. And so let's look at an example for a local match. So if we have again the constructorized version of bool with the two functions I just added, we can also do something else. We can do a local pattern match, which is like something most people are probably familiar with. For example, in Haskell, you just take some value, pattern match on this, and then continue as an expression. And now most of this is kind of similar to what you probably know already. So it's just you pattern match on this B, which is a bool, and, well, it can be either true or false, and then you just give back x0 and x1 again, because we're still defining if then else just in this different way. However, there's also something else here, which is this name that suddenly appeared here. So, I mean, you don't know it's a name, but this is something we have to add to matches in this setting here. It can be auto-generated, but usually if you want to have something that's kind of meaningful, you probably want to add a sensible name here. And if we now use this if then else function, because it's plus a regular function, we write this in the regular way, i.e. with just using the regular argument passing style as opposed to this dot way we got before. But now the problem is what should happen when we do destructurization now. Before we just took all the functions we had and kind of used them as destructors, And it turns out we can do pretty much the same here, except for a small difference. So if we did this, if we just took this to be the same thing as a function, we would run into problems when we try to go back again, because we also want it to be this transformation to be the identity if we go back and forth. So in order to be able to do this, we have to keep track about which parts were it came from local functions, from local matches instead of from global matching functions. And this is kind of what this underscore here is supposed to mean. So this is data we keep track of. We keep track of all the functions that were local in order to later be able to put them in local places again and have them appear similar as they had before. Okay, so you can now see that this time the call where the match used to be has changed quite a bit. This time it's really just a destructor call as we had before, but there's no match anywhere in sight. And if you now look at the implementation of this ITE, you can see that this is kind of at a way different place, again at the generator functions for true and false. Okay, so I'm not going to show you, but if we went back, we would get the exact same result. But now there's another peculiarity that you have to take care of in order for this to be sensible. And that is if we added so if we just add a function that never returns and just loops, and use this as a parameter here, this is not very sensible, but at the same time, since this match is supposed to be non-strict in this sense, we are because otherwise we are call by name, call by value language. But since this was an if then else, and the x0 in the only place where it's called, in the if test2 is true, you would expect this test2 to just run regularly. So, but in this case here, of course, it doesn't, because since it's a call by value language, this omega will loop before anything gets called. So there's no Boolean shortcut going on here. So let's see how this corresponds to in the match we had before. So now suddenly there's a lot of data that was added to this match that wasn't there before, which you can make a bit more readable, probably. Yeah. Okay. So suddenly a few more clauses have appeared. So one is this return clause, which just tells us what kind of return type this match is going to have. This is not really important. This is just something that appears when you go back and forth, because this data that is available, and it just tries to add as much data as it knows back into the code. But the main difference here that happens that wasn't there before at all is this using clause. And this using clause here is kind of supposed to be a closure of this. So we are closing those. So this match is supposed to be a closed function of some kind, because it has to correspond to top-level functions in some way. It has to be closed, and this is what is kind of written here. So those can be thought of as parameters for a function. There's two main reasons why we want to do this. One is that we want to preserve this kind of behavior, where, for example, if the omega was used here, we do indeed want to loop again. Otherwise, we wouldn't be able to preserve behavior between those two decompositions. Also, if we just remove this and put in omega here instead, we would also get a different program on the other side. So if you look at this here, where is it? Here, suddenly the second parameter just disappeared, because it's no longer used, because there's no closure going on about the x0 parameter, x2 parameter. And at the same time, the omega suddenly appears in the in one of the branches of the false generator function, which is quite surprising because that doesn't really make sense. If this is supposed to be something that is if then else, then having an omega, if it's so having looping behavior, just because it was false isn't really a sensible thing. Okay. So how exactly is this decomposition? So we call this decomposition diversity, but just right now I just showed you several ways to switch between programs. But there's a specific thing we do when we switch between programs, and this is this one here. So every type in our program can be thought of as a matrix, which kind of says what happens when you have on the rows are labeled by our constructors here in this case, and we label the columns by our constructors. It's the other way around. No, it's right. Columns by constructors and rows by destructors. Okay. Every cell just explains what happens when a constructor meets a destructor. And now either one of those will not be a constructor or destructor, but a generator function or consumer function. But that doesn't really matter. That's just a way to express this concrete program or this concrete type here, this matrix. So if we take, for example, the same example I just had, but in a slightly reduced fashion, we can see if we take a function type, like a natural number to natural number, as a Codata type, this is quite natural to express. So apart from having this apply, which you kind of have to do because it's kind of similar to how you would have a first-type function in Java, for example. So we have to have this kind of apply thing where we take the parameters we want to apply the function to, and then we can kind of, if we do this, we can evaluate and get a result. And of course, if you have this plus function here with one parameter already pre-applied, then just applying the second one would just be, well, applying the regular plus function, which is indicated by the lowercase instead of the uppercase. And as a data type, this is a bit different. This is what you might recognize as a defunctionalized version of this, where it's just the opposite. And now if you add a constructor, you can see that in the case of the Codata type, this was quite easy, but just adding a function. And it was, in the case of the data type, we had to add a constructor to the data type and a new case to this function, which is luckily just one. But now that we can do the opposite, we can add a second destructor, and suddenly we have the opposite problem. Adding this to a data type is easy, but adding this to the Codata type is arguably harder. All right. So to conclude, we have a few theorems about this, which are kind of important to have, which are mostly verified in Coq. So we have type soundness, of course, for our system, and those transformations between data and Codata. They preserve the typing. They are total. They are mutual inverses, and they actually preserve reduction. So we can really talk about these being different decompositions of the same program. Okay. Yeah. So I guess I'm out of time.
All right.
Thank you for attention.
Questions? All right. I'll go first to the back, then I'll come back in front.
This is really awesome. Thank you. It's illuminating to see the differences between objects and functions or data types and classes and to be able to switch between them. I wanted to ask about one possible limitation. It looks like your technique basically assumes a closed world.
Yes,
right?
It does.
And
yeah.
the actual important distinction between classes and data types is the commitments they make to people who write code that's based on your library, but that you will never see and never know about, right? Is there something you can sort of learn about this or help this in this situation from your work?
Yeah, we have thought about this, and if you try to kind of fix this by saying something like, well, we want to have this kind of different decompositions while writing the code, but once we close it up in kind of a module, we have to kind of stop doing this. And this works fine as long as you kind of expose everything you have. That is kind of a constructor or this structure. As soon as you don't do this, you will obviously run into problems. You cannot really fix this in the strict sense, but you can kind of cheat by saying something like, well, there's one main destructor for a data type, which is like the fold you have, and then adding new constructors is still possible, but you have to express every function that works on them in terms of this fold, which basically means in terms of other constructors you already have. So you can't add really, so if you had natural numbers, for example, you couldn't really add a negative constructor which switches between positive and negative numbers, because you can't express this in terms of the constructors you already have. But you could express something like a twice a constructor which kind of does successor twice.
Yeah, so I have two questions, one small and one large. So the small question is, do let bindings exist and work in your calculus? And the larger one is, this kind of symmetric view reminds me a lot of the symmetries in classical calculi. So have you looked at the relationship between continuations and this calculus?
So the answer to the first question, what was that again?
It was about let bindings.
Oh yeah. So we do actually have let bindings. We do, and they kind of just work well with the rest. There's nothing special going on there. The second question, sorry, a second, what was it again? Yeah, okay, I remember, yeah. Yeah, we have looked at this. So this is part of our future work, which you can show for a second here. Exploit the symmetry further is actually exactly what we are doing right now. So we are right now looking at a system that's kind of inspired by Seilberger's calculus of unity, which does pretty much this, yeah.
Okay, one very last quick question, because we all want to eat lunch.
So it's quite nice to say you can take the expression problem and rephrase it in terms of data and codata. And I guess part of your insight here is to work in a first order language rather than a higher order language. But to add new selectors or new constructors, what you need to do is do your swap operations. So you need an IDE.
Yeah.
And of course, what one would really like is to just be able to easily write either of these without an IDE. And you've got this internal representation that's more like a matrix that you can then sequentialize in either of these two ways. Have you thought about making that internal representation the language, which would then make it very easy to solve the expression problem?
We have, but you would have the same problem in a sense. You still would need an IDE that kind of makes it possible to, I mean, maybe you wouldn't, but. So we have thought about this because it's an obvious way to make this easier, but we haven't really thought about how we would easily express this in a sense that is still editable in a regular text editor.
So I think that's worth looking at, and then the next thing is you want the higher order functions, and so all you need to do is, like in the first talk, do the good thing and then wait 30 years.
Yeah, probably.
All right, on that note, let's thank the speaker.